Welcome to the fifth lecture video in our Class 16 series of videos. In the last video, we looked at how cyclohexane chair conformations could affect the E2 reaction mechanism. In this video, I'll be asking you to consider that you may have a competition between SN2 reaction mechanisms and the E2 reaction mechanism. And I think this is one of the areas that it's very difficult for first semester students of organic chemistry to really comprehend that sometimes you might have competition between SN2 and E2, and additionally there is some sort of competition between SN1 and E1. So let's look at, for example, 1-bromopropane and sodium methoxide in ethanol. Even though we've got a polar product solvent, we still actually prefer to do SN2 here. We've got our ethoxide, it comes in to this primary carbon, pushes the bromide leaving group out. Well, we definitely do not go through any SN1 type mechanism because we cannot, reasonably create primary carbocations in solution. So we are definitely going by an SN2 mechanism. We get 91% of propyl ethyl ether. However, we do need to recognize that ethoxide is a pretty strong base. It is a good charged nucleophile, but it's a strong base, and we indeed see 9% of an E2 mechanism byproduct, so this propene. Now, what happens as we either branch at our alpha carbon or our beta carbon? Well, that slows the SN2 reaction rate down. If that makes the activation energy for forming our SN2 product higher, we're going to start favoring E2. So as shown below, beta branching and alpha branching on the electrophile tend to favor E2. So here we have our 1-bromo-2-methylpropane, so we've increased the beta branching. Now it's actually preferable to form the E2 alkene product. So we get that in 60% yield, or 2-methylpropene, versus only 40% of this isobutyl ethyl ether. What if we branched the alpha carbon? So here we have isopropyl bromide. We know that secondary carbon electrophiles have a slower reaction rate for SN2 than primary carbon electrophiles, and so again we have a minor isopropyl ethyl ether SN2 product and a major propene E2 product. How about tert-butyl bromide, or 2-bromo-2-methylpropane? I always get students giving me SN2 reaction products for this when I throw in a nucleophile like ethoxide, but remember that tertiary carbons are too sterically hindered to undergo the SN2 reaction. So if that activation energy is just too high, we're only left with E2. We're not going to do SN1 because we're in strongly basic conditions. And so here we get our 2-methylpropene, and of course sodium bromide out of this reaction, but we're interested in the organic products. What if instead of sodium ethoxide we used a bulkier base like sodium tert-butoxide? We might write it this way or write out the bond line structure. Well, now this bulky base has more difficulty doing SN2 because it's a raised activation energy for that pathway because of steric hindrance, and so we get 85% of the E2 product and then only 15% of the SN2 product. Additionally, we could use another bulky base called lithium diisopropyl amide. This is a fairly big base. There are 2 isopropyl groups on this nitrogen with the formal negative charge, and we're going to favor E2. So our major product in this case, when we're reacting with 1-chlorobutane, is going to be butene. So, just a little bit more, and we'll be done with this class time series of videos. Can an E2 reaction proceed syn paraplanar? I promised that I would get to this example. The answer is yes, but only if there is no anti-paraplanar choice available. Here we've got what? We have an interesting molecule that has a mesylate leaving group, and we've got a deuterium substitution that will be syn paraplanar with that mesylate leaving group. They will be eclipsing. And so we ask, if we subject this to sodium methoxide and really drive it with some heat, can we get it to do an E2 reaction? And the question is, will we pluck off syn paraplanar or some alternative, hydrogen that is not quite anti-paraplanar? If we pluck off the syn paraplanar deuterium, we will get the molecule that has, two hydrogens bonded to our alkene. If we pluck off this, some other option, not quite anti-paraplanar and not syn paraplanar hydrogen, then we'd leave the deuterium behind with the hydrogen on the alkene carbons. So that's our other choice. And indeed, we see as the only product, the product emerging from the syn paraplanar state, higher activation energy, but it's better orbital overlap in the transition state than what you would experience pulling this proton off of this beta carbon, which is not quite anti 180 degree dihedral angle to our mesylate leaving group, maybe only 120 degrees difference. So still a lower energy pathway than this other choice. Something that will be useful to you, how do you favor SN2 over E2? Well, to favor SN2, you want a good nucleophile, but not necessarily a strong base, right? So you want a poor or weak base to favor SN2 over E2. What kinds of nucleophiles would those include? Those would include things like iodide, bromide, chloride, halides that are conjugate bases of strong acids. That means they're not going to be strong bases. And sometimes some conjugate bases of weak acids like hydrogen cyanide, for example. So we have our cyanide anion, that's a weak base. Acetic acid, so our acetate anion. We could even have sulfides, so alkyl sulfides are not as strongly basic as alkoxides. And also amines and these trialkyl phosphines. So here we have a secondary carbon electrophile with a triflate leaving group. We've got acetate, and we've got a nice polar aprotic solvent. So our acetate is not a strong base, so even though we have a secondary carbon electrophile and SN2 is going to be going slow, we're not going to start favoring E2 because our nucleophile is a weak base. And so we get inversion of stereochemistry. What is that AC group? It's the C double bond O and methyl. We typically, can buy bottles of sodium acetate. That's the same substance that can be found in salt and vinegar chips, and I am making myself hungry right now. That's sodium acetate, and this guy is a fairly decent nucleophile for the SN2 reaction. So with that, we've concluded our Class 16 lecture series of videos, and good luck with the questions.